Hi, Chemistry 11. So today we're going to do the last lesson of your entire course, unless I decide to throw any extra credit stuff in. The last lesson is going to be in the topic of Lewis structures and electron dot diagrams. So what is a Lewis structure? What is an electron dot diagram? These are ways of representing the valence electrons around an atom and the valence electrons as they are arranged in the bonds within a molecule. You've been taught some of the rules about valence electrons already, especially about periods 2 and 3, where, in fact, for period 1, a full shell is 2. The 1s orbital fills up with 2, and then you start filling within the second shell. And then shell 2, it's full with 2. And then period 2, shell 2, it's full with 8. And then period 3, it's also full with 8. Although, as you did see, you also have you skip past and you get the 4s orbital, and then you start filling the 3d orbital. As it says in Hebden, the rules that they're stating are being applied only to elements in periods 1 through to 3. Now, in terms of making the skill of creating an electron dot diagram, it's actually quite simple, especially if we start with an electron dot diagram for a single atom. For this skill, you start with an element symbol. Let's say we're doing nitrogen. Then we imagine a square existing around that. And the square will be about that close to the symbol. We're not going to keep it in the final structure, but just imagine that that's where we're putting things. The things that we put down are valence electrons. They're represented by dots. I normally start at the top. You don't have to. And I normally work counterclockwise. You don't have to. Working counterclockwise, I'm adding one here, one here, one here, and then one here. Notice that I don't crowd them up at the start. I add them one at a time to each side. The maximum number I can put in this arrangement is going to be 8, but I don't need to, because the valence electrons, the number of valence electrons for nitrogen is 5. 1, 2, 3, 4, and I get to the end, and now is the only time when I am going to pair up. In other words, I have 3 unpaired electrons, a valence of 3. Nitrogen will form 3 bonds, and 1 unbonded pair in any kind of molecule that you're going to create of nitrogen. So that's how to do it for nitrogen. How about the period 3 elements? Well, I wrote them out up here, alternating colors just for fun. Sodium's got 1 valence electron. I put 1 dot. Magnesium's got 2. I put 2 dots. Aluminum has 3. Notice that there's a connection here with ion charge. When aluminum undergoes a chemical reaction, it becomes an ion, loses 3 valence electrons, gives it a charge of +3. Those are the ones that it loses. Silicon has 4 valence electrons, and they're arranged like that. With phosphorus, we're doing that thing again where we double back and we end up having a single pair of electrons. Sulfur, which forms 2 chemical bonds, has 2 unpaired electrons. And chlorine, the halogen, has only 1 pair of unpaired electrons. It forms just 1 chemical bond. The electron dot diagram for neon, we show 8 dots. Now, in reality, we actually would say that the number of valence electrons for neon, at least this is the way Hebden expresses it, is 0. They define valence electrons as electrons that can be involved in a chemical reaction. Well, they aren't, because neon doesn't have any chemical reactions. So there's a kind of a disjunct there between the number of valence electrons and the electron dot diagram. Not a big deal. How about making electron dot diagrams and Lewis structures for hydrogen? When you're doing this, when you're doing any Lewis structure for a molecule, you want to draw out all the atoms, and you want to draw out the valence electrons that are being shared as dots, and then make them into bonds later. Hydrogen is what's called a diatomic element. Many elements are made to go through life in pairs. That is to say, they're the atoms of those elements bond with atoms of the same element, like oxygen, O2, nitrogen, N2, chlorine, Cl2. They bond together and form pairs if they're not reacting with something else. Hydrogen will be full when it has an outer shell with 2, and each hydrogen as a single Lewis structure is just an H with a little dot next to it. Simple as that. So let's imagine a reaction where this hydrogen right here undergoes a reaction with this hydrogen atom right here. This one brings a dot here, this one brings a dot here, and that's the electron dot diagram. Now, when we're drawing Lewis structures, however, what you do is you don't want to keep that. A pair of electrons between atoms is a pair in a chemical bond. We show chemical bonds using little lines like that. That's the final answer. Question 5C was a little more difficult. 5C and D are a bit more difficult. This is because, you're dealing with Lewis structures of polyatomic ions, right? Ionic compounds with polyatomic ions. That makes things a bit more challenging. Let's start with the easy part. The easy part is the magnesium ion. Undergoing a reaction, it has lost 2 valence electrons, and now its valence, and now we display its Lewis structure, its electron dot diagram, with no dots because it lost them. We do, however, put a square bracket around it and a little 2 plus up top, and what that shows us is that it's an ion. It's got a positive 2 charge. How about carbonate? Carbonate is formed from the nonmetals carbon and oxygen. And so now you might ask, well, what's the structure of a carbonate ion? A good general rule, maybe one that won't always be followed, but a good general rule is that when you have something that has a structure similar to a molecule and you have just 2 elements in it in a small number, like say 4 atoms, is that the least electronegative element will go in the middle. After all, it can form the most bonds, usually form the most bonds. The least electronegative element is carbon. So let's imagine a structure where we have a carbon atom. Carbonate has got 3 oxygen atoms. When you're drawing an electron dot diagram, your rules are you count how many electrons you have to work with, you fill the bonds between that are shared first with 1 pair, then you follow the octet rule for those on the outside, and then if the central atom doesn't follow the octet rule, then you go back and modify it so it does, using double bonds. Let's count our electrons first. In this polyatomic ion, carbon's got 4. The oxygens have 6 each, times 3. 6 times 3 equals 18. And we have a 2 minus charge, so there's 2 extra electrons we have to play with. 4, 18, and 2 is 24. We have a total of 24 electrons that we can work with for this polyatomic ion. Now, we're going to start putting electrons into play. Each bond will have at least 1 pair. So far, so good. Now we're going to satisfy the octet rule for the peripheral atoms. The oxygens, I mean. The oxygens are now happy. They have stable outer shells because they've fulfilled the octet rule. However, there's a problem, and the problem is that the carbon is not satisfying the octet rule. It has just 6. So we have to satisfy that problem by shifting over 2 electrons for one of the oxygens. Also, when we see that we have dots between atoms, we don't show them as pairs of dots between atoms. To make it more clear, make our diagram more clear, bonds are shown as lines. Pair of lines, single line, single line. Notice that when I had 2 pairs of dots between those 2 atoms, I showed that as a pair of lines. Each pair of dots is 1 line. I showed it as a pair of lines. That's also called a double bond. One thing I should mention about this right now is that in reality what's going on here is it's not just like one oxygen, one special oxygen is the one that forms the double bonds and the others form single bonds. In reality, electrons are distributed more uniformly among the 3 oxygens of the carbonate ion. A bond like this will be shown with a single line that is solid, and then another line that is dotted like that to show this line here is a real bond, but this one here is like a part of a double bond or part of another bond. So it's just showing you that the double bond is not really in just one place. That's the full Lewis structure. Notice that I added a -2 charge to the carbonate, putting the whole thing inside square brackets. Moving along to molecules, starting simple. The first one is NH3, ammonia. The natural first question is, all right, well, what's the structure of the ammonia molecule? What does it look like? Well, it's going to have an atom in the middle, and it's going to have some atoms around it. This is typically what you find when you have what's called a binomial. This is typically what you find when you have a binary covalent compound. One molecule in the middle, and then others on the outside. This is going to be not too complicated one because we've only got 4 atoms to play with. Each of the hydrogen atoms will only take 1 bond. Let's start by adding up how many electrons we have to work with. The nitrogen gives us 5 valence electrons. Each hydrogen gives us 3. 5 plus 3 is 8. This is a structure that makes intuitive sense. Each of the hydrogens is only going to take 1 bond. You're not going to put the hydrogen in the middle. First of all, we give at least 1 bond to each of these hydrogens. And in fact, the hydrogens are now done because they only take 1 bond anyways. We have 8 to work with. We complete this by satisfying the octet rule for the nitrogen. Lastly, we replace the shared electrons with dashes. This is the complete Lewis structure for the ammonia molecule. The next one is CCl4, also called carbon tetrachloride. And again, you might ask, well, what's the structure of this thing right here? And again, I would say, well, each chlorine will only take 1 bond. The valence of chlorine is 1. It only takes 1 bond. That simplifies things. It tells us that carbon is the only one that can be bonded to any more than one thing. Specifically, it's got a valence of 4, so it'll take 4 bonds. Kind of makes sense now, doesn't it? Because we have 4 chlorines that are bonded to the single carbon. So now let's put our carbon in the middle. We use our Cl to show that there's chlorine atoms that are situated around it. We add a pair of electrons for every bond. You know what, I guess I should have counted the electrons, right? Well, it's not too bad. Each of the chlorines has got 7. There's 4 of them. That's 28. Carbon has 4. 28 plus 4 is 32. We have 32 electrons to work with. Let's satisfy the octet rule for each of the chlorines. Well, this is a lot of dots. It's a little bit messy, you know. How can we clean that up a bit? Well, we're going to clean that up by making the bonded pairs into lines. That's a Lewis dot structure for carbon tetrachloride. Ethylene. Again, we have a similar situation. Each hydrogen will only take 1 bond, so the hydrogens are going to have to be on the outside of the molecule. There can't be any within the molecule in any weird way. So the carbons are going to be bonded together. The hydrogens will be on the outside. The next thing you might ask is one of these carbons going to have 3 next to it and the other have just 1? That's not going to work. Each of the carbons will be bonded to 2 hydrogens. This is Welder's gas, and it's a very nice symmetrical molecule. How many valence electrons do we have? Each carbon has 4. There's 2 of them. We get 8 from the carbons. And we have a total of 4 valence electrons provided by the hydrogens. 8 plus 4 is 12. Let's add in our bonded electrons for the hydrogens. We've used 8 so far. We've got 4 more. The only possible place to put them is between the carbons. This is actually a very convenient molecule because it ends up that there is no unbonded pairs. There's no lone pairs of electrons. These guys become double bonds in the middle between the carbons. I'm going to make that look nicer. And each of these is a single bond. Moving on to question 7. Question 7 deals with exceptions to the octet rule. We have the free radical, electron deficient, and a situation where we've got more than an octet. Nitrogen dioxide, well, let's see, that's NO2, right? We count the number of valence electrons that we have to work with. Well, nitrogen has 5. Each of the oxygens has 6. 6 times 2 is 12. Add 5 is 17. So we've got 17 electrons we can work with. And immediately we see that we have a problem. We have a problem because there's an odd man out. There's going to be an electron that will be on its own. Not a lone pair of electrons, but a lone electron. This is called a free radical. Free radicals are actually quite toxic chemicals. Well, let's figure out then what's the structure going to be like. And here again is a situation where at least the rule of thumb is going to work, that the least electronegative atom, nitrogen, is going to be in the middle, and the oxygens will be on the outside. So this is the O-No molecule, O-N-O. So that is the structure of nitrogen dioxide, but how does it play out with respect to the electron dot diagram? We have 17 electrons we can distribute. We start by putting at least one bonded pair between each of between the nitrogen and each of the oxygens. Bonded pair. We've used 4 so far. Let's satisfy the octet rule for oxygen next. We've now used 16 electrons, and we have 1 more to work with. Because the oxygens are satisfied, we're going to give it to the nitrogen. But the nitrogen is probably not very happy with this because it's only got 5 electrons in its valence shell. The oxygens are satisfied, but the nitrogen is not. What we can now do is we can shift one of the pairs over from an oxygen to the nitrogen. Now we're going to turn our bonded pairs into lines. And the thing I will mention to you again is this, that although we show the oxygen as one of the oxygens is being doubly bonded to a nitrogen, the other one being singly bonded, in reality there's kind of a collective of oxygen, a collective of valence electrons shared by the 2 oxygens such that there's no single double bond. There's no double bond in one place. It's like a 1.5 bond at 2 places. But typically, when you see this displayed as a Lewis structure, you're going to see a double bond on one side, a single bond on another side, and crucially, for a free radical, 1 sole electron that it's on its own that is unpaired. Boron trifluoride is what's called an electron deficient molecule. Fluorine is crazy electronegative, way more than boron. It can suck electrons away from the boron, and as such, boron has to be happy with not having a stable octet. In fact, what boron will be satisfied with is to have just 6 electrons around it, forming just 3 bonds, and that's it. No lone pairs. So What's that going to look like when it comes to the electron dot diagram? Well, each of the fluorines has got 7 electrons, 7 valence electrons. The boron's got 3. 7 times 3 is 21. 21 plus 3 is 24. We have 24 electrons to work with. Each fluorine will only take one bond. The boron's in the middle. We're going to put a bonded pair between each boron and fluorine. We have 24 electrons in total. We're going to satisfy the octet rule for the fluorines next. Lastly, we put dots with lines instead of dots for the bonded electrons. Done. The Lewis structure for an electron-deficient molecule, boron trifluoride. Okay, just had a bit of an interruption there. Xenon hexafluoride. Well, what's that as a formula? Xenon is Xe, fluorine is F. The hexa part means 6 of them. XeF6. Again, each fluorine will only take one bond. But wow, we've got a situation where we've got 6 bonds around the xenon. Notice that xenon is in a higher level period. I think it's the end of period 4, if I'm not mistaken. Its electron valence structure is more complicated, and so we say that it's not satisfied with just an octet. Xenon hexafluoride, by the way, is a very unlikely molecule. Unlikely because although it's a noble gas, it is actually forming a stable compound, and it's doing that because it's reacting with the incredibly electronegative fluorine, which is very good at stripping electrons away from just about anything. Here, all we really need to do is to acknowledge that we've got a xenon with 6 bonds, with 6 single bonds with fluorine atoms, and that each of the fluorine atoms has got 3 lone pairs. Xe, and then we just draw a nice kind of hexagon around it. And now we're going to add our dots for the fluorine. I hope that helps, and I hope that you've enjoyed this course. Hi there. As part of today's lesson, I actually also want to explore one topic in a little bit more detail, and that is molecular structure, like some of the reality behind it. So far you've seen, element symbols connected by lines with electrons, but what you haven't really got maybe as much of a sense of, or much of a real sense of as you ought to, is the actual shape of these molecules. What you see right here is a reverse of what I showed you in the last lesson. The last lesson I showed you a positive charge with negative charges that were attracted to them and were being sucked into them, and I told you, well, the electrons that are negative charges never hit the protons that are positive charges because they exist in electron shells, but bigger things with negative charges will be attracted to and touch smaller things with negative charges. Here what I've done is I have reversed the situation. I've made the object in the center the same charge as the smaller white dots, and we see what's happening is the electrons are being, or these negatively charged objects are being repelled from the positive ones. If one were to take 2 negatively charged particles and put them together, then they would be pushed apart. This is called electrostatic repulsion. Another thing is behind this as well, by the way. It's called the Pauli exclusion principle, which states a similar thing about electrons. Is basically they can't be next to each other. They're pushed apart. They can't occupy the same what's called quantum state. So electrons push apart from each other due to the Pauli exclusion principle and because of electrostatic repulsion. And this has really important results for the actual shape of the molecules. What you learned so far was about Lewis dot structure. And so I told you, for carbon tetrachloride, you take a carbon atom, put it in the middle, put your chlorine atoms around it, the more electronegative chlorine, and your dashes are pairs of shared electrons, and then you show your lone pairs of electrons as pairs of dots. Fine. But what you might not got much of a sense of is you could have come away from that thinking, well, I guess the molecule is flat and it's square-shaped. But, it's actually not quite like that. A carbon tetrachloride molecule in actually 3 dimensions looks more like, it looks like this. Here's the carbon atom. Green is often used for halogens because chlorine gas is green, I guess. I'd like you to notice, crucially here, that these electrons, these positively charged chlorine atoms with all their electron clouds are pushing away from each other as far away as they can possibly get. This comes down to the electrostatic repulsion. Those chlorine atoms have electrons around them whose clouds by electrostatic repulsion and the Pauli exclusion principle are repulsed from each other. They're pushing away from each other as far as they can possibly get. So you end up with this kind of a molecule that looks a little bit like one of those devices that's used for stopping cars on a highway, where it's got a kind of a tripod shape at the bottom and a spike sticking up. Each of those is it's called a pyramidal molecule. Methane, CH4, it has the same structure as this. Anytime you have a central atom, with 4 other atoms joined to it, no more than 4, and it's a 5 atom molecule, then you're going to get this pyramidal type of a structure. So that's carbon tetrachloride, and it's just one example. And here's how it is going to be shown if you don't use the ball and stick model. This shows the same thing. Carbon in the middle, chlorine up, chlorine down. Of course, this is symmetrical. This triangle here shows this is a chlorine sticking towards you, and this chlorine here is going away. What this is called, the theory behind this, how electrostatic repulsion drives the structure of molecules, is called VSEPR theory. Which means valence shell electron pair repulsion. In other words, the valence shell electrons, for example, of the chlorine atoms are naked. That means to say that they're not shielded by any positive nucleus. They are exposed to the outer environment, and including exposed to other chlorine atoms that happen to be nearby on the same molecule. As a result of this, the chlorine atoms, specifically their electron clouds, are pushing away from all the other chlorine atoms. There's actually a very precise shape that can be demonstrated and measured for any molecule where you have covalent bonds formed. You can actually make predictions not only about just the general shape, but actually what are called the bond angles, the angles between these bonds right here. What is that angle that is made by this line here with this point here, the carbon atom, and then branching out? Well, the answer is it's about 109.5 degrees, I think is the correct figure. Let's look at another example right here. And this one will be a little bit more clear, possibly, when it comes to what you should expect. This is that C2H4, the ethylene molecule, where you have 2 carbons in the middle, bonded in a double bond, and there are hydrogen atoms, 2 for each of the carbon atoms. Well, you see a very similar thing right here. These electrons in the middle and the double bond repel the hydrogens away, but of course there's 2 hydrogens, and the electrons of these hydrogens as well are repelled from these electrons in these shared bonds. All the electrons are pushing away from each other as much as they can. What they're doing here is actually minimizing the overall energy of the molecule. If you took this hydrogen here and pushed it towards pushed it towards the center and pushed this one towards the center of the molecule, it would spring backwards. You'd be storing energy in the molecule by pushing these towards the middle, and it would spring back to a lower energy state. Negative charges, such as in valence shells or in bonds for that matter, are repelled from other negative charges, just as positive charges are repelled from other positive charges. Look at this value right here, by the way. We remember in the circle there's 360 degrees, hardly surprising then that this angle right here divides that 360 almost perfectly into 3. If you divided it perfectly into 3, this would be 120 degrees here, 120, 120 here. This really is a flat molecule. It's called a planar molecule. This molecule lies flat. It doesn't, I mean, it has 3 dimensions to it, but the overall shape of the molecule in terms of the arrangement of atoms in space is flat. It's planar. We don't have an up-down to this molecule, just a back-forth and a left-right is a way to think about it. And you can predict the bond angle as being about 120 degrees. One other one I'll show you just to really drive this point home is cyanide gas, one of the most deadly molecules in history. Cyanide gas is HCN. The hydrogens are always going to be on the outside, by the way, recall that. They can't be on the inside because they only take one bond. And the least electronegative atom here, carbon, otherwise is going to be on the inside, joined to a nitrogen. So in fact, you can directly get the structure from the formula, HCN. And if we play this out with making our valence dot, this is an interesting situation because what you find is that we need to have a triple bond between the carbon and the nitrogen to actually explain how the electrons are distributed. That makes sense right there. So it's a very tight bond, but that's the way it has to be. So we have one single share, electrons are shared between the hydrogen and the carbon. 3 pairs are shared between each carbon and each nitrogen, and nitrogen also gets a lone pair of electrons. But again, and here we have really an exact value. The exact value of that bond angle is 180 degrees because the electrons shared between the carbon and the hydrogen, those valence electrons, are repulsed from the triple bond of electrons shared between the carbon and the nitrogen. This is called a linear molecule. So the first one was pyramidal, the second one was planar, and this third one is a linear molecule. Carbon dioxide is the same way, OCO. The molecule is a perfect line. All of this is what is predicted from valence shell electron pair repulsion theory, which again is a way of actually predicting the 3-dimensional shape of molecules. So it's one thing to come up with a Lewis structure. That's an important first step, but that important first step really is a way of leading towards understanding the overall structure of molecules in actual 3-dimensional space. I hope you found this useful, and I'm teaching this to you now because a bunch of you are going to take chemistry later, and a piece of background knowledge like this may well be useful to you in the future.